Let us continue our transport layer module. And from now on, I'll be talking about this optional component for the transport layer as a reliable data transfer. And specifically, we're going to be talking gradually in different parts of what is the principles of the reliable data transfer, how to improve efficiency, and finally, we're going to be talking about specific realization of this function as part of the TCP protocol and several aspects of the TCP protocol. And specifically for reliable data transfer, it really depends on what we're trying to achieve and what we have as a communication channel. If we had this simply like below, we had the very reliable channel, like if our network layer protocol provided us with a very reliable channel, then the process would have been simple. Because then you just send the data and then you make sure to kind of really know that this data being received on the other side and everything is simple. However, when the channel is unreliable underneath, it can lose packets, it can kind of flip the base of the packets and can do something else like reorder packets, then things are getting a little bit more complicated. And we'll try to kind of go over a few exercises, a few cases to highlight how the kind of this problem is non-trivial and a few interesting aspects of this problem. Just to get started, remember we have a sender side and receiver side. So for the purpose of this conversation, we're going to be thinking about just unidirectional communication. So just from sender sending data to receiver. What happens in TCP? They effectively have two of these elements. So there's two senders, two receivers. So just one happened to be the guy who connected, and the other guy who accepted the connection. But after they accepted the connection, there is no difference between two sides. And what happens on the sender side? The sender side accepts data from the application. And in the future pictures, I'm going to use the word RDT send. This information it's potentially disassembles the incoming data into pieces to create the packets and then sends this packets towards the receiver. And in addition to that, it's not just sending those packets like UDP would do, for example, but rather it also wants to ensure that those chunks, those packets were received on the other side. And there are several ways of how you can do this. Specifically, you can have some form of a confirmation coming from the receiver. And only after kind of sender receive those confirmation, it can move on to the next chunk or do something else. And the job of the receiver is effectively to receive those chunks and somehow notify the receiver that it has received them, or notify that something was not received, or do something else for the notification purposes. If needed, it needs to reassemble those packets in order, for example, and then deliver back to the application. And another part that we're going to be using as part of the lecture is we're going to use this finite state machine to represent different states, different transitions between the states. Some of the state will be initial one, so effectively what is this state after you starting the communication. And again, we also assume that the connection already established, and there's a few assumption about what exactly it means the connection being established. At least the sender and the receiver know about each other, but there is one more thing that I will highlight in a few seconds. And what's important here is the circles represent the states, and there's two items on each arrow. One is representing some form of event that is happening, and in most cases it will be some kind of a packet being received. And on the bottom side, below the line, is what kind of actions are happening. And in many cases, I will try to use some form of a Python program to define what's supposed to happen. Okay, so let us start with the very basic thing, kind of transfer over realizing reliable transfer over reliable channels. And in the book, if you're using it, it's called RDT 1.0. And it has very hard assumption about the underlying network layer protocol. This protocol has to have no bit errors. It cannot lose packets. It cannot reorder packets. So under all those assumptions, the protocol can be quite simple. So you simply have somehow the connection being established. I'm not saying how, but as soon as it's established, you can simply receive information from the application. So this RDT send application sending data that it wants to get reliably on the other side. And the only job that needs to be done by the sender is simply to create a packet and send it out to the network. That's it. And the job of receiver is simply receive the packet and deliver this data to the application. That's all needs to be done. Unfortunately, the real network is quite different. It doesn't really provide, and it's not actually the wrong word. It's provide no guarantees at all. So you'll be lucky if you get the packet through. Okay, so today's networks are pretty reliable in this sense. You can send a lot of packets, but even today, like on the wireless and on the LTE network, if you have very bad connection, you have very high chance that you lose a lot of packets. So the effect of the question here is what to do. You need a way to recover from all those errors. And kind of the question to you here is, as a human, we actually have the communication. We speak on a phone, and we have something similar. Like sometimes we mispronounce words, like what I'm doing all the time. Sometimes we drop in packets, like in this video, like some phrases may be not fully understandable. Sometimes, okay, this is not really part of the conversation that we reorder words in a sentence, but sometimes this can happen. So what do we do? So as a humans, we can actually come up with a bunch of ways. And let's say we have some form of communication. What we can do, we can simply reconstruct. So we don't really have to understand every single syllable, the written syllable or verbal syllable, to understand the meaning of the whole sentence. We can skip a few words, and this just highlights there's a lot of redundancy in what we're saying. Something similar may happen in computer networks. We sometimes do confirmations, not always, but for some important stuff, we actually do the confirmation. Like when we say our phone number over the phone, there is some kind of confirmation protocol to repeat what I've been just saying. Sometimes instead of confirmation, you do some form of a negative confirmation, simply saying, "Oh, I didn't receive that," or "I didn't understand that." So that's what you can do. So all of this highlights what we can do as humans, and effectively introduces what we can do as computers. So basically what we can do. So we can do some form of a checksum and forward error correction. We just introduce additional bits to the packets in order to avoid errors, or at least detect errors. We can have a bunch of types of confirmations. So this is just a kind of high-level types of this. That you can have acknowledgement that you received something, or you can have negative acknowledgement, just highlight that you did not receive something. And there's actually subtypes of these two. And to recover from errors, you can retransmit packet when you receive some kind of a negative acknowledgement, or you retransmit the packet when you time out. So effectively, if you send packet and you didn't get back neither acknowledgement or negative acknowledgement, then you just proactively send this packet again, assuming this packet was lost in the first place or the confirmation was lost. Okay, now we're getting to the first protocol. So like the first attempt, and in the book it's called RDT2. So this protocol, you already see this much more complicated than the first case, but it's still much simpler than the real TCP protocol, and much simpler than what we can actually end up doing a little bit later. So this protocol is simple in the sense that it's stop and wait. It assumes there is exactly a single packet in flight. So I mean, you send the packet and there's a confirmation of the packet. And as a confirmation, you can have either acknowledgement or negative acknowledgement. To highlight what exactly happened on this picture, so as you can see, the starting state is this wait for the call from the above. And effectively, it will wait for the event, this RDT send, which means the application send the packet, send the packet that it wants to be delivered to the receiver. Now things started to happen. So now the application is trying to create the packet, add whatever additional checksum, and send it to send this packet and move to the so-called waiting for the acknowledgement or negative acknowledgement state. At this point, again, the confirmation, the logic is you waiting for the packet to arrive, and if this packet is negative acknowledgement, you just try to resend this packet. If this packet is acknowledgement, so you receive packet and it is acknowledgement, then you back to the state that you're waiting for the call for the above from the sent packet. So on the receiver side, again, there's only one state. You're waiting for the calls to receive the application, to receive data. As soon as you receive the data, receive the packet, you kind of check the checksum. If a checksum okay, then you deliver this data to the application and just keep waiting again. If a checksum is not good, you send in a negative acknowledgement back. And I forgot to mention, if a checksum is also good, you send back the acknowledgement. And everything is fine. Seem to be fine. So there is actually a bunch of problems in this protocol. And the first problem is what would happen if the feedback is lost. As soon as the feedback is lost, either it's acknowledgement or negative acknowledgement, the sender will be stuck. So it will be stuck in a waiting stage. And like in this model, there is no way it can get out of the state. So, to effectively resolve this problem, you have to introduce the timeout that I mentioned. Because it may not happen all the time. It may need to be resolved only in a few times, but you really have to have a mechanism to kind of move from this stuck state, to get back to this wait from the call from the above and start either resending the original packet or do something else. So that's kind of one correction that needs to be done for this protocol. But that's not all of it. So one thing that let's say we've kind of introduced this timeout and everything is fine. Consider the case that kind of literally explained on a picture. So A send one packet and B send acknowledgement and deliver that packet to the application. A send in a new packet and this packet was successfully delivered to the application, to the receiver. Receiver was happy, send the acknowledgement back. But that acknowledgement got lost. So there's a timeout, and A eventually kind of detected that the timeout happened and retransmitted the packet. But B has no idea that the packet was retransmitted. It will simply assume that this packet is a new one and will deliver this packet to the application, which is completely wrong. And kind of from B's perspective, you deliver the duplicated packet, but B has no idea about this one. So to resolve this, you actually have to introduce at the very least two sequence numbers. So one is to say this is sequence number 0, this sequence number 1. So with this, you can actually distinguish between two packets. So you have to include the sequence number somewhere kind of as part of the transport layer protocol. So in this case, so you send in first packet, you get acknowledgement for the first packet, you send in the second packet with sequence number 1. If that packet with sequence number 1 being delivered to the receiver, but the acknowledgement for the packet with sequence number 1 is lost, then A is simply will retransmit the packet with sequence number 1. B will detect that the sequence number 1 packet is been retransmitted because it's different from sequence number 0 that it would have been expecting. So it's sending acknowledgement again, for example, that the packet was received. And then finally, A can start sending new packet with the sequence number 0, to reuse this one, and B will be happy to receive this packet and send acknowledgement back. So these are like two required fixes for this specific protocol. One thing that we can do, actually, one more optimization right away, is remove this NACs in the first place, because we can actually replace the NACs with some form of acknowledgement. So, for example, in the case of the last one, the P0, A sending P0, and A on the host B somehow detecting the bit error. So it has an option of either sending a NAC to indicate this one, or what it can do, it can simply send the same acknowledgement that it sent before. And if we kind of A knows about this logic, meaning if B is sending the acknowledgement of the previous packet, it would simply mean something wrong happened for the previous packet, and it can try to infer or retransmit the packet in the first place. So it's kind of additional logic that can be associated with the same acknowledgement. So one thing that I wanted to note, like already here, is A and B actually have to be in the same state. So that's this is the part of the connection setup. So the A and B initially, A has to send the sequence number 0 and B has to expect the sequence number of 0. Or vice versa, A has to start sending sequence number 1 and B has to expect to receive sequence number 1. Otherwise, they will be trying to recover from the error that never happened. And this problem will become even more complex, more necessary when you have more than 2 sequence numbers. And as I said, the second optimization is to, instead of NAC, you can send this so-called cumulative NAC. So in this case, it's not really cumulative NAC yet because we only have 2 sequence numbers. But later, effectively, we're going to be using this cumulative NAC, cumulative ACK a lot, which simply is saying it's ACK for the last correctly received packet. And from this, you can infer additional information, not just saying, oh, this packet arrived or this packet didn't arrive. Okay, now let us see all this complication stuff. So we already see there's more than 2 states now. Now we have 4 states. And this 4 states representing the initial, some kind of initial state waiting for the call from the above. And as soon as you have a packet to send, as soon as the application gives you data to send, you create in the packet with the sequence number 0. And move into the state where you're waiting for the acknowledgement for the sequence number 0 or sequence number 1. And depending on which one you receive, if you receive for the acknowledgement for the sequence number 0, you know that everything was received correctly. So now you can start prepare and send data for the sequence number 1, assuming you have data to send. If you receive acknowledgement for the sequence number 1, which means you receive acknowledgement for the previous sequence number, then you can assume there's some kind of an error, and then you have to retransmit the packet and keep waiting again. And there's additional thing that also mentioned on the slide is this timeout. And this timeout effectively discard element to ensure that you will retransmit if something really bad happened in the network. And then the bottom two states is effectively a replica of the states on the top, is just for the different logic. When you have data to send, you send with the sequence number 1, and when you're receiving with the sequence number 1, you assume the data was received, and when you receive with sequence number 0, you assume something bad happened in the network. A little bit more complex processing on the receiver side, but again, it's quite simple. It's again, you start with some state that is synchronized with the receiver or with the sender. You wait for the data with the sequence number 0. If you receive it, if it's not corrupted, you send acknowledgement back. If you didn't receive or it's something corrupted, you send acknowledgement for the previous number and move to the different state expecting a different number. And you can look in more detail at this specific example. Let us talk a little bit about one potential problem of RDT protocol. And this one is actually more than just for the RDT protocol, but rather reliable delivery protocols in general. So on the left side, we have a very basic exchanges when we have a sender sending packet, the receiver acknowledgement packets, and sometimes some of the acknowledgement are lost. If we detected this loss using the timeout, then we'll retransmit the packet and everything will be fine and communication will resume. But it really depends on the value of the timeout, and depending on how it relates to the RTT, this detection may be premature. So this is actually highlighted on the picture on the right, saying if you have a very short timeout, which is really smaller than RTT side, smaller before you can actually receive the acknowledgement, you can retransmit unnecessarily. Effectively, it doesn't really create any serious problem, but it is waste resources of the network, waste resource of the receiver, waste resource of the sender. And if you do it a lot, if you have a lot of this incorrect retransmissions using timeouts, like if your timeout is very small, then you can have really problem. And there's another problem, this one is a bit bigger problem, is utilization. So the logic of the protocol that we just described is you send one packet, you wait for the acknowledgement. You send a packet, you wait for the acknowledgement, and so forth. And if you kind of do basic calculations, like basic utilization of the calculations, so it will be really bad. So it's calculated for 1 gigabit speed of link and propagation delay of 15 milliseconds and packet size of 1,000 bytes, some kind of a typical configuration. Your utilization of this link will be at most 0.27%. So it's a 0.0027. So which is really bad. And how I calculate it, basically you can compare the amount of time the link was busy to amount of time this link was effectively waiting for something to happen. And this really relates to the RTT and the transmission time of the packet. As I highlighted on the slide, the propagation delay between continents is more than 100, like even between the East Coast and West Coast in the US, it would be on par of 100 milliseconds. And if we're talking about a transatlantic or trans-Pacific link, it would be even larger. And if you get into the account of the satellite links, those will be like on order of 300 or more milliseconds. So this is like a real problem, because in those cases, utilization will be dropped by like a few orders of magnitude more. And yet you have to have a solution for this. And to solve this problem, you have to employ so-called a pipeline. So instead of sending one packet and waiting for the acknowledgement, sending one packet and waiting for the acknowledgement, you can actually send multiple packets in the hope that all of them will be received and you get a bunch of acknowledgements back and you send more packets. So, and like eventually you actually have an objective to fill the pipe with the packets, so there's always constant flow, inflow and outflow of packets, like outflow of packets that sender is sending and inflow of the acknowledgement of those packets. But to implement this one, you actually have to have some kind of a buffering at the sender and potentially at the receiver, and depending on what kind of service you have to actually provide. And with the pipelining, you can really increase the utilization. And depending on what the pipeline size you pick, so for example, if I pick the same example, but instead of sending one packet, I have this pipeline of 3 packets, we can significantly boost the performance. So instead of 0.027, now it's moved 3 times more. It's 0.08%. Not great in this specific example, but it's at least 3 times more than what we had before. And effectively, to utilize all the link that is available, you can calculate how many packets will be needed to actually fill the pipe. But one thing to note here is the number of packets is not fixed. You cannot just pick the pipeline on 5, pipeline of 6, pipeline on 15, because the pipeline is a dynamic parameter and it really depends on the RTT between the sender and receiver. And the RTT is actually not stable, and because your path can change and delays can change because of various parameters. So this is another problem that needs to be addressed by the real transport layer protocol. Okay, so I'll finish this introduction to reliable delivery here. Just remember, to implement reliable delivery over unreliable links, you have to have ability to detect errors. And to detect errors, you can either use some acknowledgement, absence of acknowledgement, like in form of acknowledgement. You can use NACs, you can have a cumulative ACs, you can have a selective ACs that we're going to talk next time, and maybe some additional mechanisms that you can imagine. You have to have mechanisms to recover from errors. So obviously you have to have a mechanism of retransmission, but you also have in addition to just retransmitting, you have to have ability to distinguish between retransmitted packet and the new packet, because without this ability, you can have a problem. Like because you cannot look in the state of the sender and know the same state at the receiver side, because you're only observing incoming packets and observing what you can send out. And from all the information that you're receiving, you have to know for sure what you're doing. And for real system, kind of if you think about efficiency, you have to consider a few things. So first of all, you have to have a pipeline. And the pipeline potentially need to be adjusted properly for the RTT. You also have to have some form of estimation of retransmission timeout, because if you just randomly pick the timeout value, this can be either too much or too little. If it's too much, you unnecessarily kind of slow down the transmission. If it's too little, you may have send unnecessary transmissions. Okay, I hope it was interesting, and the next part will be about improving the efficiency of this specific protocol and how exactly we can actually implement this pipeline in the simplest way.